Today in the Physics Funhouse, we are investigating the principle of refraction. Refraction is the bending of a wave as it travels from one medium to another. For instance, as it goes from air to the glass of this magnifying glass. The light gets bent, and that's what's causing this image to be different when you look at it through a magnifying glass versus when you don't. So we're going to do a couple of refraction demonstrations real quick. Not all of them, because none of them are going to video very well, but some of them we can do with the lights on. So let's investigate the bending of a wave as it travels from one medium to another. One of the classic demonstrations of refraction is the bending straw, or in this case I'm using a colored pencil, in a glass of water. If you look at that pencil in the beaker of water, it looks like it is broken. Like right about here where the water ends, it looks like the pencil is broken, but it's not. It's just a normal green, aqua green actually, colored pencil. And if you kind of move around, you can see a lot of cool different effects created by the refraction of light as it goes from the water to the air. Water in a spherical vase will bend light as it passes through it, causing it to be turned into a lens. In this case, the image that we're looking at is inverted since it points upside down. That arrow on the board points up. When you look at it through the vase, it points down due to the bending of water. That's something we're going to work on later, tracing ray diagrams for lenses or things that are approximately lenses to see how images are formed like this via refraction. An excellent example of refraction is a simple prism. This is a triangular prism. Right now you see 2 or 3, depending on how steady I hold the camera, arrows on the whiteboard, but in reality there's only one arrow on that whiteboard. As the light enters the prism, it is reflected off the faces and refracted as it goes from one medium to another, so as it goes from the air into the plastic, and that results in the formation of different images. We can investigate the principle of refraction a little more closely by using a single beam light source. So this is just a light with like a little picket fence thing in front of it. Kind of looks like that, so that only a single beam of light is created by the light source. That's something that we can actually trace and visualize without the extra light causing interference or reflections. And so if I take this single beam of light and I put another material in it, this is a semicircular piece of acrylic, then we can see the refraction. Well, that's kind of cool. Of the light as it goes from one medium to another. Notice that not all the light is refracted. Some is reflected as well, and that's always going to be true. In any interface, there's 3 things that could happen. One is reflection, one is refraction, and the third is that it just gets absorbed as thermal energy. And so like if you put your hand in front of light, like most of it is just absorbed as thermal energy. If you put something that is black in front of the light, most of the light is absorbed as thermal energy. So let's investigate this refraction thing a little more closely. Put it kind of like there. So notice that the incident light right here is bent, and it's bent away, or excuse me, towards the normal, like this, and then when it reaches this surface right here, it is refracted again. And so the refraction is going to occur both as the light goes into the piece of acrylic and as it leaves it. I can kind of simplify it by turning the flat edge like that so that it is normal to the light. So like there's not a whole lot of change going from here to here because the incident angle is 0. And then you kind of get a better idea of what happens here. As the light goes from the acrylic to the light to the air, you can see that it bends just a little bit away from the normal. Okay, so let's kind of do a real quick demonstration of kind of how we do the geometry behind refraction. We're going to learn more about the details later on, but while we've got a good visual of refraction, I'm just going to kind of show you like where these angles are so that you have like a reference point to kind of think about. So I've got a rectangular prism here, and it's kind of hard to see the light inside of there, but we can see the light entering and we can see the light leaving, and then we can kind of trust that in between light's going to go in a straight line. hopefully. And so I've traced this edge right here of this little acrylic block, and then what I'm going to do is I'm going to kind of like trace this ray out with some lines. So I'm just going to put some dots on the top edge of that ray, and I'm going to do the same thing for the refracted ray over here. 2 dots because 2 dots make a line. And then I'm going to trace the other edge of this real quick. Okay, and so that's what the light's actually doing as it goes through the acrylic. And so if I draw the ray that's going in, let's turn on the lights real quick. So if I trace the dots that I drew, here's the ray that is incident on the block. And then the outgoing ray after it exits the block would be right here. And what you'll kind of notice about those 2 rays is that they're parallel to each other because these 2 surfaces of the block were parallel to each other. Useful for illustration. In between the 2 surfaces of the block, the light must have done something like this. So there's the refracted ray of light as it travels through the acrylic block. So just like we did with reflection, when we measure angles with refraction, angle in versus angle out, we always do it from the normal. And so remember that a normal line is perpendicular 90 degrees to a surface. And so I can compare these angles by using a protractor, figuring out exactly where 90 degrees from the surface of my block was, and then constructing a line that is normal to the surface of the block. So this is the normal line, just like we did with mirrors. So remember we do that because not all of our surfaces are straight. These are nice flat surfaces, but earlier I was using something like this. You can't measure an angle relative to this surface. It's curved. And so you have to use the normal line relative to that surface at a particular point and measure your angles from there. And so the incident angle is the angle between the incident ray and that normal line. And then the refracted angle is the angle between the refracted ray and that normal line. And so in this case, the incident angle, theta I, is greater than the refracted angle, theta R. What that eventually is going to tell us is that light travels slower in my little block compared to the air surrounding it. And we'll get into the geometry between these angles in our next video. So investigating this a little bit more generally, when a wave is incident on a new medium, like going from air to a piece of acrylic, there's 3 things that could happen to the energy of that wave. Some of it could be reflected, and so you can see a little bit of reflection occurring here at the boundary between the air and the acrylic block. Some of it could be transmitted, so you see some light goes through it. This is where refraction would occur, would be during transmission. And then the third possibility is that some of it could be absorbed as thermal energy. And so like if you put your hand in a beam of light, after a while your hand would start to feel warm. The amount of which of those 3 things happens depends on the nature of the incident material, so in this case air, and then the new material, in this case acrylic. And so when you shine light on things that are black, for instance, you get mostly absorption, very little reflection or transmission. Things that are transparent like this, you get a lot of transmission, and there's all sorts of cases in between. The other thing that affects the amount of reflection and transmission is the incident angle itself. Right now, with a low incident angle, you'll notice that just a little bit of light is being reflected, not a whole lot, and a lot of light is being transmitted. If I increase the incident angle, if I turn it this way, what you'll notice is that this beam is getting a little bit brighter, and this beam is getting a little bit dimmer. And so with an increased angle of incidence, more of the light is reflected, less of the light is transmitted. I increase this more, so you'll notice at this angle that this beam is almost as bright as this beam. And so the steeper the incident angle is, the more reflection you get compared to transmission. One example of this in your everyday life would be like the surface of a lake or a pool. At noon, when you look into a pool or lake, typically you can just see straight down into the water. But as you get closer to sunset or sunrise, the angle of the sunlight is steeper in relationship to the surface of the water, and you get more reflection. And so right at sunset, if you're standing over here and you're looking into the lake, you're not going to see a whole lot of light transmitted from the lake. You're going to see reflected light from the surface. And so the surface of the lake would look like a mirror, and you would see like the trees and stuff around it, rather than seeing down into the water. One special case to consider is the case when the new or transmitted medium, in this case air, has a greater speed of light than the original medium, in this case the triangular block of acrylic. And so we're not looking at this surface, we're looking at this surface as the light goes from the acrylic back into the air. And so you'll notice again that at this surface, at this interface, some of the light is reflected, this beam right here, and then some of it is transmitted. Most of it is transmitted in this case. This angle right here, this incident angle, will be relatively low for the acrylic air interface. But as I increase that angle, notice that eventually we get to a point where all of the light is reflected and none of it is transmitted. All the light is reflected, none of it is transmitted. This is referred to as total internal reflection. Internal because this usually happens inside a particular thing, like in this case a triangle, because that's what you would normally need in order to get the original or incident medium to have a slower speed of light than the transmitted or new medium, in this case air. And so at this angle, the refracted angle is essentially exceeding 90 degrees. And so if the refracted angle is bigger than 90 degrees, well, 90 degrees would just mean that it would run parallel to the surface. You can't have a refracted angle greater than 90 degrees. And so all the light gets reflected, none of it gets transmitted. And so that's a condition, again, that we refer to as total internal reflection. And it has a lot of uses, one of which I'll demonstrate here in just a second, which is a fiber optic cable. And so when we reach that angle, which is referred to as the critical angle, and so the incident angle, when that occurs, is called theta C, or the critical angle, then all the light's reflected, none of it gets transmitted. So let me grab the fiber optic demonstration and show you that. So one cool application of total internal reflection is called a light pipe. And so this is just a piece of acrylic, which is bent in this like real cool curvy shape. And one end is right here, it points up, and the other end is over here, it's pointing towards the whiteboard behind it. And so I'm gonna shine a laser into this thing at the top, and you should be able to clearly see the laser light on the table right now. But when I shine it into the light pipe, what you'll notice is like the whole thing starts to glow when I get it lined up correctly. And you don't see laser light on the table below, you see laser light on the whiteboard at the other end of the pipe instead. And so what's happening here is that the light is undergoing total internal reflection inside that little acrylic light pipe, and it never actually leaves the pipe, except where you kind of see it glowing at some of the edges until it gets to the end. And so it's basically trapped inside the light pipe until it comes out the other end, and then you see it on the whiteboard. Let's turn it towards you for just a second. Okay, so now you should be able to see the end pointing towards you. I'm going to shine the laser You see the laser glowing. And so one cool application of this is to send signals and messages and information across long distances. So you could do something like Morse code, or probably more useful for a computer, something like 1 0 1 1 0 1 0 0 1, binary code like that. And so essentially what this is a fiber optic cable. Fiber optics is just sending light signals across long distances. Things like this are really, really cheap. And then you could group lots and lots and lots of them in real tiny ones together into strands a lot cheaper than you can make wires out of copper. And so total internal reflection is basically what gives us fiber optic communication, which is kind of sort of becoming more and more the backbone of our communication system. So what we want to be able to do with refraction is explain how it occurs, explain how total internal reflection occurs, and then be able to predict angles of reflection and refraction, and then later on use it to explain how lenses produce images. And so those are the things we're going to work on over the next few days in Physics 2. Till next time, ta-ta.